we're going to start off with an interesting new topic. It's about kernels, and this is also related to your lab, and we'll see how many existing ideas can actually be packaged or viewed slightly differently to give you a lot more expressive power. So you'll realize that what you have learned till now actually is quite powerful. Okay, so let's recall the perceptron update rule, which was largely, let's say, a linear function. Fx is w transpose phi x, can have a b if you want, and our update rule was wk plus 1 equals wk plus some adjustment based on a misclassified example, especially its so that its unsigned distance becomes a really unsigned. Now we are going to do the following. We are going to put wk plus 1 in the place of the function and really see what happens. Okay, so we are going to basically take this guy, put it here, and see how interactions take place. So your fx after an update will look like this, right? You can write it yourself. So the dot product of wk plus 1 with phi x is the dot product of wk with phi x plus the dot product of phi x y. So let's distinguish between these two. Let's say this is x prime, y prime, x prime, y prime, the misclassified points, misclassified point. Okay, so what would fx look like? Wk, so let's say this is after the update, wk transpose phi x plus y prime times phi x prime transpose phi x. I just inserted wk plus 1. So I want you to list down observations about each of these two components. What do you observe? What do you observe about this component? What do you observe about the second component? Yes. What's the first component? So let's give this an index. So this is fk plus 1, means one that is had been updated. This is f. Yes. And what about the second component? So second component is measuring some kind of similarity between a misclassified point x prime and the query point. So this is a query point, query or test point. This is a misclassified point. What is this component measuring? Similarity in the sense of some dot product, the dot product between the phi of x prime and the phi of x. That making sense? Can I expand this further? What if I now substitute for fk x in terms of fk minus 1x. Okay, so it will be again some fk minus 1x plus y times phi x prime dot product with phi x plus y double prime, maybe some other point before that, dot product of phi at that point with phi x. Right? Do you see this happening? As I keep applying this, what is the form of what is really the form of fk plus 1? Let's say we start with some w. Okay, it's a good point. So let's just try and abstract this. What does this look like? So f0, it will be some f0x based on whatever initialization I had of w, right? Plus summation. So I am going to abstract these two into some summation. Summation over all the points that mattered in terms of adjusting the perceptron. Summation over all the misclassified point x prime by comma y prime of the dot product of phi of x prime with phi of x with y. I mean the y prime basically is always trying to adjust for the sign. Now if a point gets misclassified multiple times, then it will count those many times, right? So you could, if you want, just say times count x prime, count that x prime was misclassified. It's a misclassification count. Does that make sense? It's not all points. I'm just saying, yeah, right. So you could you're saying you could generalize it to all points, right? So you could now say this is just summation over all x comma y, x prime comma y prime of this term with count weighing the number of times it got misclassified. Right. At the point we decide to pick as well. You may iterate over all points and say, well, I'll pick the point which is the most misbehaving unsigned distance, right? So unsigned distance should be unsigned, but you may say, oh, if it is very negative, the most negative unsigned distance is what I'll pick. So that's one way, or the other is just change the way you iterate. Right. So this is depending, you're right. So this count is basically overloaded because the count also is conveying the way in which I iterated over the points. Right. So just to be consistent, what we have on the board is x prime y prime. Let's just call it x prime to be consistent. And just to again, misclassification count based on update policy, right? That is your point. But what I want to draw your attention to is this dot product. Okay. Now with this dot product, the function basically is like, function is only in terms of dot products. I can actually get rid of the phi and call it some k, also denoting kernel. And I want to now impress upon you that actually you don't need phi at all in this view of the world. Okay, so I'm saying that, well, this entire expression can be replaced by this similarity kx comma x prime. Okay, I'll call this dot product similarity as kx comma x prime. So my classifier is basically a weighted sum of these similarities with all the points or the misclassified points weighed by how much they were misclassified. And this is the function. How do I change my update? Well, one way I can change my update is this count times y prime, or even just the count. I'll just call it alpha. Okay, I'll give it a name. This alpha x prime is a weight associated. Okay, so just to give you an idea of what's happening, let's look at this view again. So you identified a misclassified point, and now you basically folded this in to your classifier. So the misclassified point is folded into classifier, and now your classifier has moved. The next query point is misclassified because you are comparing the new point in its dot product, in its relation with the previous point which is folded into the classifier. So indirectly, right, misclassification indirectly computes similarity. Okay, so basically this, think of this this previous one as the x prime and think of this as the x. So it basically computes the similarity x comma x prime through the classifier. Okay, and now the classifier will no longer be parameterized using w's, it will be parameterized using the alphas, the alpha weighted sum of the similarities. Okay, this is the key point. So you have the k, and k is now parameterized using alpha x prime, and the story continues. You again fold this point. This is what you have done. This point folded in. And that basically is folded in now through alpha x, its own weightage, right? Okay, so now let's just outline this algorithm called the kernel perceptron. And as I said, this kernel perceptron, so I want you to write this I mean, in case you have seen it, great, just a recall job for you. But this should be independent or not expressed. The idea is should not be expressed in terms of phi and w, but expressed in terms of, yes, or should it be expressed in terms of k, but this has two arguments, k has two arguments, and What are the new parameters? Alphas. So please do that. So on suggestion is that since misclassification based count depends on the update policy, you could actually treat count as a function of not only of x prime but also of all the previous weight, whatever the parameters. I think that's not so important. I hope if you understand the spirit. Now let's write kernel perceptron directly, and as I said, write it without involving phi, without involving w anywhere. The first kernel classification learner was presented in 1964, pretty old, but somehow it takes time for things to get together and create some coherent story. So the story I'm unfolding is not necessarily the story that has, the way things have actually chronologically happened. Now we are looking at things in a different perspective. What all will you keep in mind? Where all does 5 get involved in the regular perceptron? When we check for whether a point is misclassified or not. There I should not be involving phi anymore. Can I write that purely in terms of f? F is this. You can, right? If the sign of f doesn't agree with the sign of the point, then the point is misclassified. That's possible. Update rule. What will you update now? Will you update w's? No, you are not allowed to. What will you update? You'll update f, but what will you update? To update f, what will you update? Alphas, right? And what will your update of alpha? What does alpha look like? Count. So at every step, how much may you update alpha by? 1. Okay, so the idea is fairly simple. For every xy, if fx y is less than 0, the signs disagree, then alpha x equals alpha x plus 1. That's it. So the understanding is, the implicit understanding here is that fx is exactly of this form, summation over all the points of alpha x times x prime. Let me put a prime here. So alpha x prime k prime. Sign, but if fx prime y prime is less than 0. Does it make sense? What will be in this scheme of things, what are alphas actually initialized to? So implicitly, alphas are 0 initially. That's basically f, that is f is the same as saying that f0x is always 0, identically 0. Okay, so this is the simple algorithm. You could also have a b term there, and b is what, I would recommend that b is used because b is what will account for a non-zero initialization of the w's, the equivalent of w's, right? Initially, you don't want to start with 0 w's. So in practice, you would use a b because b is basically the weight for bias component of x. It is always set to 1. So in practice, you have this. So b, the additional thing, which b could be a random But in often what you do is you sample B from a normal distribution centered around mean, some variance sigma. Sample it. I hope you know how to sample. Have you done sampling in your 215? Okay. What is the main tool you use in sampling? I don't know. Sampling numbers. From write a computer program to sample number. What would you do? I mean, yeah. One is to use pre-built functions. But what's the basic idea? You have to use a cumulative density, cumulative CDF, right? Cumulative distribution function. Anyways, that's not part of discussion here. So, right.
That is the alpha again is dependent on the way you update. So that definition.
Yeah. So all we are saying is this is the definition that will be used throughout. It's just a definition. I mean, so initially alpha zeros you just evaluate it this way. So this is the definition of f in terms of the alphas. That's a good point. Yeah. It's like, so that B is basically accounting for the effect of F0, the bias term. So we will, I mean, see now, this is really very rudimentary algorithm. I mean, it also is not that ineffective, but we'll see there are better. I mean, yeah, we are not happy that B is not getting updated. That's why I started with the earlier version where there was no B. Yeah. No, I'm saying it's you sample from the uniform. It's not uniform distribution. You just sample from it. Linear. No. F0 is linear, but I'm saying B can be one point. It's just some value. That value can come from. So I mean, if you're getting confused with normal, just I'll just delete it. Some value. I mean, just and I said it's often centered around 0. The way you sample, you don't want it to deviate too much from 0. But this is really not, again, the point was you have to just sample B. So let's just say B. Okay. So I think it's important to focus on the kernel part here, and now we get going with some very interesting additional properties of this K. So how do you ensure convergence? I mean, I think B becomes useful when you look at convergence, because you're not really happy with 0 W initialization in your original perceptron. So let's look at an example kernel, right? K. So let's see this. Okay, I want everyone to do this. Notebooks, please. 5x. This is your 5xy, 5xi. Let's say this was my original 5xi. I want you to tell me what the form of, say, k xi comma xj will look like. Yes, everyone. What will be the form of k xi comma xj? What does this phi xi have? So this is 2-dimensional. Phi is 2-dimensional. I mean, xi is 2-dimensional. It takes the first component of xi, multiplies that by square root. Second component multiplies that by square root, and then also takes the product of these two components, multiplies that by square root. Takes the square of the first component, say takes the square of the second component. How many dimensions does it have? Okay, so let's say phi, so here phi x is a function from R2 to R6. For the time being, just ignore this first sentence. Phi x goes from R2 to R6. Okay, now tell me the form of k xi comma xj. Simple algebra. axi comma xj is nothing but phi xi dot product with phi xj. Tell me the form. Either is okay. So far, I mean, it's okay. They're both not are. So we're dealing with real phi's. Phi is the real space. So phi xi transpose xj and phi xj transpose xi are going to be the same. But I'm happy that some people are concerned about the order of the dot product, because it is making some assumptions when you show that kind of interchange and assume equivalence. So what is this? 1 plus 2 times xi1 xj1 plus 2 times xi2 xj2 plus 2 times xi1 xj1 xi1 xj1 xi2 xj2 plus xi1 square xj1 square plus xi2 square xj2 square. Is this fine? So the observation you now make is that xi is a vector. Can I write this entire expression in terms of xi's and xj's? Okay, so it turns out, so I can show that this is nothing but xi1 transpose, sorry, xi transpose, yes, yeah, is this what you have, what you're saying? Square of the entire thing or the square of xi xj transpose? Okay, so anyone wants this to be elaborated upon? What have you observed here? This x1 transpose x2 in general, or xi xj, xi transpose xj is nothing but xi1 xj1 plus xi2 xj2, right? So if you now add a 1 to it and square it, you will get basically all those interaction terms. So for these terms, for example, this xi1 xi2 xj2 will contribute to this, will contribute to this part. So this component will contribute here, 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 and the other component xi1 xj1 will contribute here, this part, the cross product term, and here. Okay. I hope this is obvious to all. So what I want to impress upon you is that the dot product in a two-dimensional space, this is a dot product in a two-dimensional space, has led to a kernel which corresponds to a dot product in six-dimensional space. This is the key. A kernel is this is a dot product in six-dimensional space. So what I was trying to say is, xi comma xj turns out to be basically 1 plus xi transpose xj the whole square, and there are a couple of interactions that are taking place in the original two-dimensional space xi, right? So this is an interaction taking place in xi, whereas what we are enjoying is the advantage of the kernel, which is computed in a six-dimensional space, and this kernel is nothing but the dot product of the phi in a much higher dimensional space. So this is a dot product in R6, and this xi xj is dot product in R2. So this is the idea of kernel, that you can have dot products in lower dimensional spaces translated or projected into dot products in higher dimensional spaces, which means that even though computing, now how easy it is to actually enumerate these components. I mean, basically enumerate them and then kind of redundantly multiply each of those terms. On the other hand, if you just take 1 plus xi transpose xj the whole square, it's much more efficient to compute. Can you contrast the number of computations? How many computations would this take? A dot product in R2 will be order, I mean, let's say in general, I'm going to make this in some d-dimensional space, will be order of 4d. What about the dot product in this higher dimensional space? And let's again not call it 6. What is, if 2 becomes 6? Actually, let me not call it d here. This is the original space k. Let's use the word k here. So I have a dot product in k where k equals 2, and now I'm looking at dot product in a space which will give me a, let's say, exponent 1 plus xi transpose xj raised to d. So let's say this is the term I was looking at. So this will be dot product in R. How many dimensional R? Some polynomial term involving k. It's a polynomial term, right? So 2 became 6. K will become some polynomial expression. Okay, at least what I meant is it's certainly not linear. It will not be linear. 2 will become 6, 3 you can work out, it will be in, I think, the 10s or 20s. So the dimension quickly grows. Okay, so it suffices to say that it will be a non-linear or superlinear growth in k. Okay, but the advantage is just by taking a 1 plus xi transpose xj raised to d, I can get the same effect. So how much this computation 1 plus xi transpose xj raised to d, how quick is that? It's basically order k only, right? I mean order k plus some cost involving d, exponent, I mean raising it to power d. So will it be order k log d? Okay, so that's much cheaper. Oh, sorry, order k plus log d, obviously. Okay, and what do you get? So this is just polynomial. So there are all these other kernels. A polynomial kernel is a general thing. Kxy equals 1 plus x transpose y raised to d. So I am going to list these down on the whiteboard. They will be useful. So linear is what we have seen so far. X transpose y. Polynomial is 1 plus x transpose y raised to d. Now there is something called the RBF kernel. RBF stands for radial basis function. Okay, and that is e raised to minus of norm of x minus y norm square divided by 2 sigma square, where sigma is basically the width of the RBF factors. And I am just going to give one illustration. So in the RHS, what you have done is enumerated phi. So here for example I have taken phi to be x square, z square, xz, all the three components, all these interaction terms, right, and in that larger space I get a linear separator. On the left hand side I have been lazy. I said I am not going to toil myself in the larger dimensional space. I am just going to compute k x comma y as 1 plus say x transpose y is to whatever, this would be squares, whatever. So the point I am trying to illustrate is that in the original space you actually get a non-linear separator. In the high dimensional space you get a linear separator. So this should be apparent from all of these. This is the lower dimension in which I am getting a non-linear separation. So just with respect to say x1 and x2, the points could have been like this, positive and negative, and my separator might have been something like this. Whereas if you look at the space of the phi's, if I could just construct a phi here, a space of phi's, this might have been say 3-dimensional, and here somehow I have managed to project them in such a way that I get linear separation. That's true with all, that's true with any kernel, any non-trivial kernel. Linear is basically a trivial kernel, you are operating the same space. Okay, so kernels operate in high dimensional implicit feature spaces. They are also called implicit because I don't really need to compute the phi. So what is implicit is phi, without necessarily computing the coordinates of the data in that space. You just compute the kernel function, and this is often cheaper. Okay, so let's try and understand a little bit more what is the kernel or the gram matrix. It's a matrix of all dot products. Take m data points, take dot product for every I with every j, so k xi xj. So my first claim is that if the k was indeed obtained using some phi, there exists phi for which it was for this existed, then this matrix must be symmetric. This k must be symmetric. Is that obvious? So my eye is on k now. Kernel perceptron was just one example. So what are the properties I expect this k to exhibit? So one is this kernel function itself. So k xi comma xj is supposed to be dot product in some higher dimensional space phi. On the other hand, I have this calligraphic k, which is a matrix of dot products for data points I equals 1 to m with data points j equals 1 to m. This is what we call the gram matrix. What are the properties I expect this to have? What are the properties I expect the k function to have? So we have two views, right? This is the gram matrix or the kernel matrix. This is called the kernel function. Now the gram matrix requires you to enumerate some points. Kernel function is on any pair of points. What properties do you expect if I tell you that each of these entries is of this form? Each of these entries is a dot product. Yes. So I have mentioned one property, symmetric. Do you think they will be symmetric? Agree? Why will it be symmetric? So we are talking about reals, right? And so I would expect kxi xj and kxj comma xi to be the same. So it's symmetric. What is the other property you expect? What are the properties you know about matrices? Real, symmetric, singular, non-singular, full rank, square. Is it square? It's square. What else? What other property do you know? Positive definite. Do you think this will be positive definite? Positive definite or positive semi-definite? Okay. So some of you are suggesting let's kind of verify. Positive semi-definite. Okay, we'll also abbreviate it as PSD, and that's a question mark. Why do you think it will be positive semi-definite? Give some justification. Okay, so he's saying to show that the gram matrix is positive semi-definite, can we look at some V transpose calligraphic K V? Let's look at its form. Is this visible, this chalk? No, so I'll just use it. V transpose calligraphic KV. Write down the form. What will it look like? Right. So what will it be? So each Kij is phi transpose xi, phi xi transpose phi xj. Yeah. So I mean, if you want to write it in the naivest way, what will this look like? Summation over all the indices in I, in V here, all the indices in V here, into the components xi xj, right? Okay, so this will basically look like, yeah, so I will use B there, so V okay, so you'll have all these components bi, bj, phi xi transpose phi xj. Now, is there a way we can write it differently? This is sum of product. Can I write this as yes, any other form that I can write this in? Norm, which norm square? Okay, so what do you observe here? You have said that we can actually write this as a dot product of two weighted vectors. So think of two weighted vectors this weighted vector is summation over I bi phi xi. Okay, all the components of phi are written in the form of a column vector, so it transpose. Okay, and another which is a column vector summation over j bj phi xj. Right, so this dot product, this is already transposed. Okay, so this is exactly what we have written here. The first component, this is a row vector. Think of this as a row vector. Think of the second one as a column vector. So dot product is written as an inner product. So basically it's inner product of some linear combinations of phi's. What do you expect that to be? But I mean, you expect that this indices I and j are basically notional. I mean, I could have replaced this I with a k, this j with a l. So nothing stops me from saying this is also the same I, because it's just a running index summing over all the entries, summing over all the i's. Right, so this is actually the same vector. Is that clear? So it's basically like a dot product of bi summation bi phi transpose xi with itself, and that is nothing but the norm. The 2 norm, which will always be greater than or equal to 0. So that's what makes it positive semi-definite. So if, again I repeat, if there exists a phi, then k we have showed is positive semi-definite. Now if I give you a positive semi-definite k in the sense calligraphic k, can you show that there exists a phi, some phi? So I give you this matrix, it's symmetric, it's positive semi-definite. Can you reconstruct the phi? And that's what we did for the case of 1 plus x transpose y raised to d, right? What did we do here? We showed that phi xi, which is 1 xi1 root 2 xj1 root 2 xij, oh no, sorry, was this correct? We had 6-dimensional expression xi1 xi1 i2. So we had all these six terms. We showed the existence of this phi such that 1 plus xi transpose xj square can be shown to be a kernel. Now I want to do the same thing with a matrix. I am giving you a matrix, I want to construct a phi. So for any data set x1 to xm, and for any gram matrix, it must be positive semi-definite, right? So we can show that you can compute multiple decompositions, and one decomposition is a Cholesky decomposition. You can also singular value decomposition. So all these decompositions, what do they give you? Some orthogonal matrix, some matrices with some form whose product will be the original matrix. Specifically, when you do this decomposition, if it's positive semi-definite, you can show that it can be decomposed as U sigma U transpose. Sigma is a diagonal matrix, and U is orthogonal. Okay, you can also make it orthonormal by pushing things into sigma, or you can consider R to be just U sigma raised to half. So what we can show is that if K is positive semi-definite, there exists an R. On the other hand, if K is positive semi-definite, there exists R such that this matrix K is R transpose. That's a summary of what I've written on the slide. And what is this R then? What will you see this R as? Phi. This R is basically a phi that gives me back the kernel. So you'll view this R as, what will be the rows of the R? So I'm saying this will be that big matrix phi, the matrix phi that you have seen in regression. What will be the form of this phi? So each row would correspond to one example, one feature. So you'll have phi x1, phi x2 and so on, and RR transpose will have phi x1, phi x2 and so on. Right? So let me show you an example. So you can actually simulate this. I'll give you the code. This is a simple Scilab. So exp minus xi minus xj. This is the square divided by 10 is how I computed kij entries. Now I have actually, for some choice of points, these 7 points, we have the k matrix computed here. Okay. So this is how I computed k. Now I want to rediscover a phi. The illustration is how I go from a phi to a k to some other rediscovered r, which is like, it may not be the original phi, it may be some phi tilde. Think of this as phi tilde. Okay. So this is the original phi that generated. I do the singular value decomposition, I get u and d. D is basically sigma. I get these weights, and now I do the following. I take square root d into u transpose. I am saying that these are my phis. The columns, these columns in this matrix R are my phis. I mean, I hope this example is clear. I just used real data to compute this. You can check that. You can check that this will give you the same dot product as the original real phi. Right? This is my phi tilde. If you want, just put a tilde here. So this was based on some phi, kxi, comma xj, which was some real phi xi transpose phi xj, whereas here I have some phi tilde computing the dot product. Yeah, so this is, you're saying the original phi. Yeah, okay, good point. Okay, so now the lesson is as follows. I am saying that this decomposition, eigenvalue decomposition that I did, I can actually apply to any general. I give you a new functional form, right? Can I show that the radial basis function also has an actual phi? So I am suggesting that instead of enumerating x1 to xm, think of eigenfunctions. So eigenvalues is when you have a finite set of x1 to xm. That's what we did here. I did basically took you through eigenvalue decomposition. But now to show that something like the radial basis function is actually a valid kernel, we can use something called eigenfunction. To show phi exists. What is that phi? I don't know, but I can try and do that. Okay. So now instead of going through that, we have something more ready made for us, which we can directly leverage, and that's called the Mercer kernel. Mercer kernel is just extending all this eigenvalue decomposition to eigenfunction decomposition. Okay, so k x1 comma x2, you can show, so let's say k x1 if you can show that it is of the form alpha j times phi j x1 phi j x2 summed across all values of j, where the j indices could potentially go to infinity, which means there are countably infinite number of indices, and alpha j's are all greater than 0. Okay, so that's the analogy. Alpha j greater than 0 is the analogy of the eigenvalues. So if your matrix is positive semi-definite, what do you expect the eigenvalues to look like? All the eigenvalues are non-negative. All the eigenvalues are greater than or equal to 0. So that's the same expectation I have. This is the equivalent of eigenvalues. And such that the summation of all the alpha j's squared is finite. That's also a requirement. Now I won't get into the technical details here, so you can show that positive definite kernel such that for every data set you get this, you always get a positive definite gram matrix, and a Mercer kernel which is expressed in terms of summation over these phi j multiplications across x1 and x2 for possibly countably infinite indices. These two turn out to be equivalent if the input space has some nice property called compactness. And what is compactness? It's like equivalent of closed and bounded. So the input space is closed and bounded as well. Again, we'll not get into this closed. I hope you understand. We have always dealt with closed intervals, bounded intervals. But the point is that I'm not going to give you a tool based on this. So this is just some theoretical underpinning. So there is a Mercer's theorem, and this is actually the tool you need. Okay, everything else is to kind of justify why this theorem is here. So k x1 x2 is a Mercer kernel. That means it has an eigenfunction decomposition if integral of k x1 x2 for all values of x1 and x2 for all square integrable functions gx, this integral is always greater than or equal to 0. Okay, so this is for all square integrable functions gx, which means that if you do a gx square dx is less than infinity, finite. Okay, so I just want you to show. So what we will do is we will show this for the case of polynomial kernel. Pardon? For all square integrable functions, for every square integrable function. No. For any given any square integrable function, this should be greater than or equal to 0. So again, I remind you, what are we doing here? This inequality is the positive semi-definiteness, right? Greater than or equal to 0. What are this G? What is the place that G is serving? This B has become G, but it has now become Gxi or Gxi Gxj. Okay, so this is the correspondence. And the use sigma or ud u transpose, right? ud u transpose. This d was like your alphas greater than or equal to 0. So everything has a correspondence. Only thing is now we may have an infinite number of indices here, and there, in fact it may be uncountably infinite. So we are now replacing the summation with integrals. So what we will do is, just this is the Mercer's theorem. For any Mercer kernel, there exists a phi. So if your kernel is Mercer, which means that this is always greater than or equal to 0 for all square integral functions g, then there exists a corresponding phi, such that phi transpose phi is k. Okay, again, you basically now your phi may no longer go to a finite dimensional space. So it might go from the original space Rn or Rk, instead of R6 it might go to a infinite dimensional space, but that infinite dimensional space has something nice called Hilbert property. So it will be basically Hilbert space, right? What is Hilbert? Go and ask Hilbert, but then we will not, again I do not want you to bombard you with more jargon. It is an inner product space. It is a space where inner products exist, where every Cauchy sequence, which is increasingly, where the sequences in which points come close enough, they converge. So that is a Hilbert space. But again, we are interested in the tool. So here is what we will do. Okay, I just need 5 more minutes. I want to show that x1 transpose x2 is a Mercer kernel. Okay, so I listed some kernels there, but instead of polynomial, I'm going to deal with a simpler kernel, which is just xi x transpose y raised to d, not 1 plus x transpose y, just x transpose y raised to d. And what I am going to show is that this integral for any square integrable function g will always be positive, and the idea, the spirit is exactly the same of eigenvalue decomposition. Okay, so let us just do that. I have this integral over all values of x11, x12, and we are dealing with some say t dimensional input space x1t. Okay, let's assume that x1 and x2 are in say rt. So I have this polynomial term, and moment I look at x1 transpose x2 raised to d, so basically then I am looking at the summation over all indices of xi, xj, xi, yi raised to d. So same thing here, x21 integral x22, x2t, these are all the indices, x summation over t, xit, so x1t, x2t raised to d. This is the original term I am dealing with. But now I can expand this. So what will the corresponding terms be? All those terms, right? D factorial divided by n1 factorial, n2 factorial, nt factorial of x1j, x2j raised to d. So when I expand this, I mean, you have done combinatorics, right? Basic discrete math. This should have been covered in discrete math. So n1 factorial, n2 factorial, nt factorial, these are the number of terms that have this particular exponent nj associated with x1j, x2j. So product for nj, each of these, x1j, x2j raised to d. So not t, nj. Okay, the rest is basically what? G of x1, g of x2, dx1, dx2. The additional constraint is that the summation of the ni's should be d. Basically it's like distributing d objects in t different bins. How many ways can you distribute t objects in t different bins? This is exactly the term, right? Now the rest is simple. I mean, once you have written this, you have integral of finite sum. Could you write integral of finite sum as a sum of integrals? Could you push this integrals inside? Okay, so those are the gymnastics we'll do. We'll say, okay, I forgot the summation. There's a summation here. The summation is all over all values of n1 to nt. So this summation, I'll try and pull it out. Then what happens is you'll have two integrals. I mean basically integral over g component, x1 component, x2 components, but both will look exactly the same. I want to draw your attention back to what we did with phi here, right? Bi phi xi square, norm of b, I mean summation over I, bi xi, norm square. We realize that these two are exactly the same terms, they just have different indices. So once you pull out the summation, you will realize that xi and xj are just notional. I mean integral over xi, integral over xj is basically going to be the same. Okay, so it's the same idea here. What you will have is summation over n1 to nt. So I'm just showing you the basic idea. You'll have d factorial divided by n1 factorial to nt factorial times some integral over x1 gx1, some integral over x2 g of x2, and you realize these two are exactly the same. That's square, and you know that g is square integrable, so that's how you basically get this whole thing to be finite. The same idea. So if you understand the finite case, the infinite case is simply a generalization of that, the infinite dimensional space. Okay, so that's why I went through, I spent some time on the previous one. Okay, so under finiteness conditions, integral of sum is the sum of integrals under Fubini's theorem, and that's because of that theorem I can pull out the summation outside. Now same principle I am going to apply here. I will get a summation outside, integrals inside, a product inside, and I realize that the integral over the x1s, the x1 component, and the integral over the x2 components are separable and they turn out to be exactly the same. Is that clear? So I'll have an integral over x1, x11 n1, x12 n2, x1t nt gx1 times an integral over x2, x21 n1, x2t nt gx2. Of course there's a dx1 here and a dx2 here. And this is nothing but the square of the same integral. Okay, so this is what it turns out to be. This entire complex thing, basically this turns out to be this much simplified expression. So thus we have shown that you basically get positive. This whole thing is going to be always greater than or equal to 0. So we have shown that x1 transpose x2 raised to d is a Mercer kernel, right? And now you can show by similar simple logic that now you take positive combinations of these x1 transpose x2 raised to d, right, take positive linear combinations, they will all be the Mercer kernel only, right, they will give you basically Mercer kernels, all of them will sum to greater than or equal to 0. Okay, so I mean we will do some of this, I mean continue on this post midsem, but what I want to impress upon you is that this seemingly simple choice. So what for today's lab I want you to really appreciate that these seemingly simple choices of kernels actually have a lot of underlying machinery which have mathematical justification, but the simplicity gives you a lot of power because you can actually deal with high dimensional spaces implicitly. Okay, so it's something we'll linear kernels, polynomial and radial basis we have done. So there are closure properties of kernels, etc. Again we will continue on this post midsem. In the lab today, I mean I had basically the lab in mind. I'll quickly go through. I talked about how we can kernelize perceptron. Similarly, you have a kernelized logistic regression. I'll do this in the lab, and in the lab we'll also do kernelized ridge regression. Okay, so because those are part of the lab. I mean that's just simple mathematical manipulation of those specific forms. But again, the kernel that they will all invoke is the same kernel. I mean the same family, from the same family, which have some nice properties. So we'll have only the basic idea behind a kernel for midsem, the fact that it corresponds to a dot product. I will, as of now, I'm not going to test you on the Mercer theorem. So Mercer theorem won't be a part of midsem. But simple questions on kernels certainly you should be able to answer because it's also part of today's lab. In addition to kernel perceptron and kernel ridge regression, kernel linear regression. So we'll see you in the lab today.